So now it is my pleasure to introduce you to the speakers today. I'm delighted to be joined by Michael and Mario. Michael obtained his PhD in astrophysics from the University of Cambridge, researching X-ray emission from accreting black holes. Prior to Optibrium, he held previous postdoctoral position at the University of Cambridge, UK, and a research fellowship at the European Space Agency, all focused on the use and development of data science tools to analyze complex, noisy datasets. He now leads much of Optibrium's research in generative chemistry and AI methods. Mario is a principal scientist at Optibrium. He has a background in computational chemistry with a PhD in natural sciences from Caltech. Since joining Optibrium in 2017, Mario has led much of the company's research and development efforts into metabolism prediction, developing new models based on quantum mechanics and machine learning for predictive modeling. With that, I'll hand over to Mario to get things underway.
Yeah, thank you. And hello to everyone from me as well. And we thought that we'd open this presentation up with a bit of a discussion. And actually, I'd like to start with asking Michael a question. But before I ask that question, I would also give some background to my question. So obviously, models have been an important part of Optibrium and Startup since the beginning. And we actually have two tabs or modules that include a variety of different classification models, regression models, and these tabs namely are the metabolism tab and the models tab. Now, many of these models which we do have, they are trained using our tool called AutoModeler, which is also available in Startup. And I could talk about the AutoModeler for an hour at least, but one of the features which I really like in AutoModeler is that it enables you to choose a specific modeling method that suits your data in a way that is not biased at all. Now, going towards my question, I just noticed that one of the methods which we don't have in AutoModeler, and you actually will talk about this specific method in your presentation, is the neural network or neural networks. And I was just wondering, what is your opinion? Why haven't we used neural networks as a modeling method that much at Optibrium?
So it's a good question. Before I answer it, I'd just like to mention that I've noticed that I'm wearing exactly the same clothes as I am in my official picture. And I'd like to reassure everybody that I do, in fact, own more than one set of clothes. This is just a coincidence. On the neural networks point, like we kind of nowadays have this kind of default assumption that, AI is magical and can solve all problems instantly, and it's not worth even looking at other methodologies. But with tabular data in particular, so data in big tables where you have rows of molecules and columns of descriptors, neural networks haven't been necessarily competitive with more conventional machine learning models like tree-based models, random forests, gradient boosting, that sort of thing. And the reason for that is that one of the biggest advantages neural networks have in general is their ability to make use of structured data. So when I say structured data, I mean things like images or text data, things where the relationships of the individual data points within that data, the relationships between those things are important. So the relationships between words in a sentence has an enormous amount of meaning on the final meaning of a sentence. If you shuffle them, it's a completely different sentence now. If you shuffle the columns in a table, it makes no difference. It's the same table. You've just moved some columns around. Those columns have no positional relationship to one another. And neural networks, unlike other kinds of models, can take advantage of this kind of structured data, and they can use that structure to inform their predictions. This is why neural networks are much better than other methods at things like image classification or text generation or protein folding, that kind of thing, where you have a really complex problem and solving it relies on understanding the relationships between the data structures that you're using. That has started to change in the past sort of 5, 10 years as machine learning and deep learning in particular has advanced. You've probably heard a lot about graph neural networks in recent years. So graph neural networks, rather than working from a set of descriptors, work directly from the molecular graph. So rather than giving it a big table full of numbers, you just give it molecules. And it learn that graph neural networks can then learn from the actual structure of your molecules. They derive their own representations and they can use that to make predictions. So rather than being reliant on a table that you've made of descriptors, they can do this sort of on the fly stuff. So some of this is things that we are looking at building in the future. A lot of this is actually stuff that I'm going to talk about in the main presentation. But it goes some way, I think, to explaining why neural networks haven't been the answer to this kind of predictive modeling for most of Optibroom's history.
Yeah. So you also mentioned data structures. So leaving neural networks aside for a second, we often, when building QSAR models, we do have tabular data. Is there an a priori method how to look at the data and decide, oh, this data is really good for random forests, or maybe this data is good for Gaussian processes, or something similar?
It's it's really difficult to give a precise answer. You can look at a data set and say, oh, this is a really small data set. We don't want to be fitting giant neural networks with millions of parameters on this. They'll just overfit. And you can look at a huge complex data set and say, okay, linear regression probably isn't the ideal model here. We probably want something more sophisticated. But drug discovery is an enormously complex field. There are so many different kinds of endpoints, so many different data sets in terms of number of rows and columns and number of complexity of the model that you need to build, the sparsity of the data, the noise, that sort of thing, that it's really almost impossible to a priori say this model is going to do best on this data set. You can make some general statements about when certain classes of models are likely to do well, but most of the time there is no real substitute for just actually testing these things. And again, it's something that we'll touch on later about the importance of testing a diverse set of models so that you make sure you're getting the best performance possible.
Yeah. So I guess my next question would be about consensus modeling, but I also happen to know that you're going to talk about this in your presentation. So I think maybe this is a good time for us to stop, and I'll give the floor to you so you can continue on with your presentation.
All right. Thank you very much.
Yeah.
Okay. Yeah. Bring this to the main body of the webinar. So this is all 90% of this is based around this paper that we recently published in JCIM on improving predictions of molecular properties using a combination of graph featurization and heterogeneous ensemble models. So I'll get into more detail on both of those things as we go through the slides. Yeah, the paper is published in JCIM, so you can access it there. There is a preprint on arXiv if you don't have access to the actual journal. That will go into all the nitty-gritty that isn't covered in this talk. And if you'd like to have a look at that and contact me afterwards, I'm very happy to chat through some of the fine detail as well. Starting at the beginning with the motivation, I like to boil this right down to the basics of what QSAR modeling is. Fundamentally, it's the process of going from a molecular structure to a predicted endpoint, some ADME property, for example. QSAR modeling is everything that happens in between. So traditionally, that comes in two steps. Step one, you have to quantify your molecule. You can't just shove a picture of a molecule into a model and expect to get good predictions out. You need to convert your molecule into a set of numbers that we can use for machine learning. For example, this could be a set of 2D descriptors. Um, or yeah, there are lots of different kinds of descriptors you could use, but the classical approach is to take a set of 2D descriptors. In Stardrop, for example, we use a combination of whole molecule properties and smarts patterns to get a bunch of descriptors out. Other methods are available, and exactly which set of descriptors will perform best will depend on the task that you're looking at. Once you've quantified your molecule, you've turned it into a set of numbers, or you have a big table of sets of numbers for a large set of molecules, you want to put those through a predictive model. So this could be something like a random forest, a neural network, it could be linear regression. Any number of different algorithms could do this. So if we want to get the best possible prediction out, we have to optimize these two steps. We want to optimize how we quantify our molecule, and we want to optimize the models that we use to make predictions. Now, obviously at Optibrium, we're making software for other people, primarily medchems, people who don't necessarily want to get into huge amounts of detail in how they build their models. They just want it to work. So an important requirement for us is that we can offer cutting edge performance straight out of the box without needing, a team of data scientists to come in and fine tune everything and spend weeks on it. We want any user of Stardrop to be able to build powerful models. So to do that, first off, we have to have a model or a modeling framework that is capable of giving really good predictions. We need it to be extremely flexible so that it'll work on every endpoint in every data set. And we also want it to be able to quantify the uncertainty that comes out. We want to be able to highlight the best predictions and show where the model is less confident so that you can identify the most important places for adding new data or where you want to be more cautious about the model's predictions. I'm not going to get into uncertainty in great detail in this webinar. I believe we have various other materials on the subject, and we'll probably come back to it because it's very important. So, step one of optimizing our modeling framework. So I mentioned this before, it's ensemble modeling. So some of you may have heard of ensemble modeling before. The most sort of common example is random forests. And what ensemble models do is they make a prediction by combining predictions from individual smaller models. So in a random forest, for example, you have a set of decision trees, and the forest is making a prediction from the combined estimates of all the individual decision trees. So this is the most common type of ensemble model where you have a set of weak learners, the decision trees, that make individually not great predictions, and you combine them to make a single strong learner, which makes a much more powerful prediction. On the other hand, uniform ensembles of strong learners, so for example, 5 random forests at the same time, are commonly used for uncertainty estimation, and they also have the benefit of reducing the variance in your predictions. Now, this doesn't actually just apply to machine learning. This applies to humans as well. So there's a phenomenon called the wisdom of crowds, where if you get predictions of something from multiple people independently, they start to get more accurate as you add more and more people into that prediction. So I think the first time this was noticed, at least scientifically, was in this paper called Vox Populi from Francis Galton in 1907 about a crowd of people at a country fair guessing the weight of a cow, and they recorded 700 different estimates for the weight of this cow from a whole range of different people, most of whom were presumably not experts on the weight of cows. Nevertheless, the mean of their estimates was within 1% of the true value. So it kind of demonstrates the effect that we're talking about here with ensemble modeling. Now, I've mentioned a couple of times that we're talking about heterogeneous ensemble modeling, not homogeneous ensemble modeling. So that's ensemble modeling using different types of models. There are a few reasons for this, and the most important one is that there is no single best model. So Mario mentioned this before, but when we're training a model to fit some data, we don't necessarily know in advance which kind of model is going to do best. And because drug discovery is such a diverse field, it means that there is no single best model. Like, this is a general principle in machine learning. It's referred to as the no free lunch theorem, that there is no one algorithm that will do optimally well on all problems. As an example here, I'm showing in the top panel some simulated data from a sine function, from a sine wave, fit with a Gaussian processes model, which fits a nice smooth curve to it. Looks very much like the original sine wave I used to simulate the data, and a random forest, which jumps all over the place and is quite clearly fitting the noise rather than the data a lot of the time. It's overfitting. In the bottom panel, however, I've got a step function. It's got a very sharp drop in it that the Gaussian processes model just can't fit because it likes smooth curves. It can't cope with a discontinuity like this. The random forest, on the other hand, loves discontinuities. It's a tree-based model. It doesn't care about smooth curves. It likes sharp edges. But if we add them together, we're actually getting a slightly better model in both cases. So you can see that by adding these two models together, you reduce some of the overfitting of the random forest, and you keep the ability to fit sharper edges. Now, this is a very simple example with just two models in it, but you can see where I'm going with this. You get this kind of the whole is greater than the sum of its parts effect going on. So by adding more and more models together, you're reducing variance in your predictions because you're getting more and more independent estimates. So you can look at the mean rather than having your models jumping all over the place, trying to chase individual data points. And you're also starting to remove what's called the inductive bias of your models, the bias that is built into your individual algorithms because of the way they're constructed. So like random forests have a bias towards discrete steps, and Gaussian processes have a bias towards smooth functions. Again, we mentioned this before in the discussion, but it bears repeating, I think, that deep learning is not automatically the best solution for every problem. And we shouldn't just reach for AI approaches without considering the problem at hand carefully. This goes in with what I talked about before about no one model is the best model for every problem that you're looking at. So deep learning for us it's part of the toolbox, but it's not the whole toolbox. So if we don't explore other options as part of our modeling, we limit the ultimate performance that we get. And what we want is a diverse toolbox that contains every algorithm that could possibly work for our problems. So the modeling solution that we've come up with, we're referring to internally as the MetaModel, and this is an ensemble model that combines a diverse set of machine learning algorithms. So we take, for example, neural networks, gradient boosting, different regression models, random forest, nearest neighbors, Gaussian processes, and so on. And we add new algorithms to this all the time. We remove ones that aren't performing very well, and so on. We take all of these algorithms. In many cases, we take multiple copies of each model with different hyperparameters. We take all of them, we train them on the data, and then we use a meta model to combine their predictions. So we're calculating a weighted mean of their individual estimates, weighted by how well they're doing on validation data. And we use that weighted mean as our final prediction. Similarly, we can calculate the uncertainty from the weighted variance of their predictions. So that gives us, an estimate of how confident the model is by looking at how much the individual submodels agree with one another. I said that we're including multiple copies of algorithms, so we've tuned various different models for different data sets so that we know they'll do well in different regimes. And that means that if we have different copies of them with different hyperparameters optimized for slightly different regimes, when we fit this model, we can remove the ones that aren't performing particularly well on the data that we're looking at. It's effectively a simple form of hyperparameter optimization, but it means that most of the time we can skip the very the very expensive step of running hyperparameter optimization for all our individual models. We have a similar version of this for categorical models, a very similar set of algorithms, obviously excluding things like ridge regression, but bringing in other more classification-focused models. And there we're looking at weighted probability estimates from the classifiers. So we combine them to get final and more accurate probabilities out. When we train the meta model, we keep the test set fully held out throughout. That's not used for training any of the submodels at any point. And we split the training set into a different validation set and train set for each submodel. So each submodel is trained on a slightly different portion of the training data, which helps to increase the independence of the submodels. The more independent those models are, the better, because they're giving slightly different predictions that way. And having the same prediction multiple times, like the exact same prediction multiple times, doesn't help us. We want more independent estimates. This submodel validation set is used to set the weights. The exact weighting scheme that we use depends on the metric. So, for example, if we're using mean squared error, we would weight them as the inverse of the error. And then once we've trained everything, the MetaModel itself is evaluated on the test set, which is, as I said, it's fully held out. So there's no sort of contamination or data leakage going on. If we look at a couple of simple examples here, again, just with 1D data, the top panel is showing a very simple, almost linear function. The blue lines are showing different submodels from the ensemble, and the black line is showing the MetaModel prediction. So you can see that while the submodels themselves are overfitting wildly in various places, the MetaModel itself is very close to the true function, as close as you could expect to be given the noisy simulated data that I've used here. Then if you look at the bottom panel, it's a much more complex function, and several of the models, like the simple linear regression models, are badly underfitting this data. They don't match it at all. Because they're doing so badly, their weighting drops effectively to zero, and the MetaModel performance is unaffected. You can see it does still a really nice job of fitting close to the true function. We observe this in more complex data sets as well. So this is from real data. This is the CACO2 data set from Wang et al. 2016. And what we're looking at here is the prediction performance as a function of the number of models in the ensemble. So if we look at the orange line first and start from the top right, we have a full-size ensemble with sort of 60 models in it, and then we're iteratively removing the worst model. The orange line is showing the mean performance of models in the ensemble. And as you'd expect, as we remove bad models, the performance gets better and better and better until we reach the single best model, and that's it. The blue line, on the other hand, shows the performance of the MetaModel ensemble doing their kind of aggregated weighted prediction. Now, first off, you can see that the error here, so this is mean absolute error on the y-axis, you can see that the error is significantly smaller for the MetaModel than it is for the average of the ensemble. And as we go from right to left, as we iteratively remove models, first we see the same behavior. The model gets better, the aggregate prediction gets better as we remove poor performing models. But at a certain point, we reach a minimum, in this case, around 20 models, and then the error starts to increase again. So what's happening here is the variance of the model predictions is going up again because we've made the ensemble smaller. And that shows the power of ensemble modeling here. It's because you're using an ensemble, you're getting better predictions out by including more models, even if those models aren't as good as the single best model in your ensemble. And taken together, this gives us a really powerful method for making predictions. So we've got a good, powerful model framework for making our predictions. We haven't talked about how we quantify the molecule yet. So we still need to optimize that part of this. And what I want to talk about today is using learned versus fixed descriptors. Most of you will be familiar with fixed descriptors, I'm sure. This is a kind of your standard molecular descriptors, things you might find in RDKit or in StarDrop. Things like molecular weight and log P and so on, and then what substructures are present in your molecule. Any set of pre-compiled descriptors based off molecular properties, physical modeling, and so on. So this is what QSAR modeling has traditionally relied on, these pre-compiled descriptor sets, and they are designed generally to give you good coverage of molecular properties that are likely to be relevant for a wide range of problems. However, similar to how there is no one machine learning algorithm that will optimally fit all data sets, all endpoints, there is no one set of descriptors that is optimal for all modeling problems. There is no set of descriptors that will be uniformly ideal for every endpoint in drug discovery. It's just too complex a field. And the space of all possible molecular properties, all possible descriptors is huge. There are presumably hundreds of thousands, if not millions, of different numbers that you could put in. So you can't possibly use all descriptors for every problem because you'll be unable to separate signal from noise. You'll overfit everything. So how do we get around this limitation? I mentioned graph descriptors in the, I mentioned graph neural networks in the discussion with Mario at the start of this. And there's been a lot of work recently on building graph neural networks that can predict properties directly from the molecular graph without needing any fixed descriptors at all. So you take your molecule, you put it into the GNN, it passes through various layers of that network, and that network learns what we call a latent representation or a latent vector of molecular properties. So it's on the fly deriving, learning which properties of the molecule are relevant for the property that we're trying to predict, the endpoint that we're trying to predict, rather than having to derive a general purpose set of descriptors. However, there are limitations to this. Not all descriptors can be easily derived on the fly from a limited data set. If you have a small data set, it's difficult to derive more complex properties from that, which might actually be very relevant to your problem. Um, and GNNs have their own sort of inductive biases, the model biases that are inherent to the way they're constructed. Quite often they'll struggle with sort of large scale whole molecule properties. They tend to propagate signals over smaller substructures along the bonds within the molecular graph. And they quite often don't have enough time or the sort of network structure to pull out a whole molecule property like molecular weight trivially. The way people often get around this is, for example, in the ChemProp model, which I'm sure many of you will have heard of, is to combine the GNN with conventional descriptors, general purpose precompiled descriptors. Um, so you use your GNN to derive the latent vector of molecular properties, but at the same time, you're bringing in general purpose descriptors that hopefully will cover the weak points of that. So ideally you're getting the best of both worlds. You're getting a good set of general purpose descriptors that will work reliably, and then you're using the GNN to derive task-specific descriptors or task-specific features that will push your modeling to the next level, extracting just the most relevant information. The only limitation really from this point on is that when you're using a GNN like this, those descriptors, both sets of descriptors, then go into feed-forward network, prediction head. So this is a basic neural network, commonly referred to as like a multi-layer perceptron, the basic fully connected neural network, which is then used to make the prediction. This is perfectly reasonable because you need a full neural network from end to end to be able to train the model like this, to train the GNN. But it does limit the performance of the model. Because you're restricting your modeling algorithms to just this one model, the feed-forward network, you're limited to the performance of that model. And we saw before that there is no one modeling algorithm that will do optimally well on all possible problems. So how do we deal with this? Well, it turns out that once we've trained this model up, we don't necessarily need the feed-forward network at all. We have a model that can produce these features on the fly, this latent vector of molecular properties, but we can actually just remove the feed-forward network prediction head. This is a weak point of a model like ChemProp and other GNNs, because the feed-forward network will frequently underperform relative to, say, gradient boosting. So if we just remove it, then we've got ourselves two sets of descriptors, one that's general purpose and one that's task specific. And in principle, we can use those with any model we like. Which brings me to our combined modeling framework. So this is how we stick those bits together. Let's just refresh what we need for this. So first, we need a set of diverse machine learning algorithms so that we have ideally like optimally performing models for our specific problem. We need a set of general purpose descriptors so that we're giving good coverage of molecular features. And we need a set of learned descriptors from a GNN to identify the key features that are relevant to our specific problem. So we've constructed our combined modeling framework like this. We have the GNN, we have our descriptor calculator. We've trained the GNN. We're using the ChemProp GNN for a lot of this. We've trained that in advance. Then we've removed the prediction head. And then we're combining these two sets of descriptors, inputting them into the MetaModel ensemble so that we can aggregate predictions from a diverse set of algorithms. Now, I want to talk about some of the results that we've got from this that we've published in the paper. To do the benchmarking here, we've used the MoleculeNet benchmarking dataset, a set of datasets, I should say. It includes a wide range of different datasets. A couple of these we've skipped. QM7b, one of the quantum mechanics datasets, only includes 3D coordinates and not SMILE strings, so we can't really use it with this framework. And the PDB bind dataset it's a protein binding set. It includes both ligands and proteins, which is not really what this model was designed for, so we're skipping that one as well. Leaves us with 6 regression datasets and 9 categorical datasets covering a very large range of number of compounds and number of tasks within those datasets, from things with a few hundred compounds to things with a few 100,000 compounds. And we're comparing 3 different models. Initially, we're looking at ChemProp with the GNN and RDKit descriptors. So the GNN I'm referring to as the MPNN here. This is the message passing neural network, which is the specific type of GNN architecture that ChemProp uses. And I will use that throughout the results section. We're comparing that with the MetaModel with the same 2 sets of descriptors, external descriptors and the GNN descriptors. And then we look at the MetaModel with just the external descriptors to see how that compares, to see whether the bringing in the learned descriptors from the MPNN is boosting the performance or not on any given problem. So if we look at the regression results first, these are showing the sort of mean metric for every task in a given data set and normalized to the performance of ChemProp. So all of the metrics are either mean absolute error or root mean squared error, which means that in every case, lower is better. And what we can see is that on every data set here, at least one flavor of the MetaModel is doing better than ChemProp. And in most cases, both flavors of the MetaModel are doing better. So on 5 of these 6 data sets, MetaModel is highly significantly better. On the lipophilicity data set, it's marginal. The p-value is 0.05. And we can also see that on several data sets, bringing in the MPNN descriptors, the learned graph descriptors, boosts the performance. It doesn't always, and there's a real divide here between the quantum mechanics data sets and the more conventional sort of pharmaceutical style data sets, physiochemical data sets. Now, this is most likely because the RDKit descriptors are more appropriate, more optimized for physchem data sets than they are for quantum mechanics data sets. So being able to learn new descriptors is really useful for the QM case because RDKit isn't offering good coverage of those properties. And it's less useful or actively harmful on data sets where RDKit is already doing very well. If we look at the classification data sets, we see a similar picture. The performance is either very similar between ChemProp and the MetaModel, or the MetaModel is significantly better. So on 6 of the 9 data sets, the MetaModel is better, 3 of these are highly significant, and the other 3 are marginal. On only 2 data sets is ChemProp significantly better. So that in this case, we're looking at the AUC from either the precision recall curve or the ROC curve. So higher is better on this graph. And these 2 data sets where ChemProp is better, these are both toxicology data sets. And the reason that ChemProp is doing better here is because these are sparse multitask data sets. They have a lot of different endpoints in them, and those endpoints have gaps. So the MetaModel, as we've constructed it here, is designed to do single target modeling, one thing at a time. ChemProp can do multi-target modeling, which means that the effective dataset size, if you're modeling all the endpoints in the dataset at the same time, is much larger than if you're doing them one at a time, because you don't have to remove all the rows with gaps in. This is fine. This is sort of expected behavior. If we restrict ChemProp to single target modeling, the difference goes away or the MetaModel outperforms it again. So it's a promising avenue for sort of future research for us, but it's not something that we're worried about at the moment. This is the kind of behavior that we would expect to see on this kind of data set. It's also something that's much more suited to our kind of imputation style modeling. So our Sorella software is really good for these kind of data sets. It's not the specific thing that we're trying to optimize for here. We also wanted to look at what happens if we just use the graph descriptors, just the MPNN descriptors from ChemProp without any external descriptors. to see how that affects the behavior of both models. So on the regression data set, both models are worse than they were with the external descriptors, but the the drop in performance from the MetaModel is noticeably larger. So we can conclude here that Chemprop is relying and making better use of the GNN descriptors than the MetaModel does. But it also implies that Chemprop is making less effective use of the fixed descriptors, which is kind of what you'd expect. Chemprop is trained to derive those GNN descriptors, so you kind of would expect it to be making optimal use of them. And we see a similar thing on the classification data sets, although the Chemprop performance on average is actually slightly better on classification data sets here without the external descriptors. The MetaModel performance drops slightly aside from this one data set, the MUV data set on the left-hand side. Um, my guess for why this happens is that it's caused by overfitting. The MUV dataset is extremely skewed and hard to model. So if you're bringing in more descriptors, you're giving it more potential for overfitting. So my guess is that by removing the external descriptors, you simplify the problem. None of the models do very well on this dataset, so I would take it all with a pinch of salt. But overall, yeah, the picture is consistent with what we saw on the regression models, that Chemprop is not making particularly effective use of the external descriptors, but it's making very effective use of the learned descriptors, whereas the meta model is kind of the other way around. It makes okay use of the learned descriptors, but very good use of the external descriptors, which is why overall, on average, it will outperform Chemprop. But if you remove the external descriptors, it struggles relative to Chemprop. So this brings me to my summary slide. We've talked about how we can combine heterogeneous ensembles and GNN featurization to build better QSAR models. So heterogeneous ensembles allow us to prioritize the best performing models for any given problem, reducing variance and inductive bias from the models, while using the Chemprop MPNN as a featurizer allows us to combine general purpose descriptors with powerful learned descriptors while still being able to use a range of different machine learning models to maximize performance. Combining both of these things together with the MetaModel Ensemble modeling framework gives us a tool that will match or outperform Chemprop on most data sets, with the notable exception of large, sparse multi-target data sets, which we have an entirely different modeling solution for that will also do extremely well. We've also noticed that the benefit of including the graph descriptors varies. So it depends on the data set that you're looking at. If you're looking at something that is already a close match for your general purpose descriptor set, then they're unlikely to help. If you're looking at something that is harder to model with a fixed descriptor set, then it's quite possible that the GNN features will give a significant boost in performance. And if you'd like to read more about this, I'll refer you to the paper again. We also have a blog post on our website that you can read if you are interested. It's a little easier to read than the paper itself. And I think that brings us to Q&A.
Thank you, Michael. Thanks, Michael and Mario, for such a thorough and well-considered presentation. As a reminder, if you have any questions, please add these to the Q&A panel at the bottom of the screen, and we will work through as many as we can with the time left. Any questions we don't have time to answer, we will try to follow up via email as soon as we can. Michael, so I have a few questions already coming for you. So the first one is, what is the smallest or largest data set that MetaModel can handle?
It's a good question, and it's not one that there's a trivial answer to, at least on the small end. The ability of a machine learning model to model a small data set will depend on the complexity of the data set. If you're trying to derive something trivial, you can get that from a very small number of data points, 10 to 20 data points, say. But if you're trying to derive something that's very complex, then you need more and more training examples to get a good model out. The meta model will run regardless of how many data points you put in there. It's not going to crash unless you have, say, one data point. But no machine learning model will do well without enough examples to learn the function. On the higher end, we benchmarked it on data sets with a few 100,000 rows in them here for the paper. We've taken the MetaModel up to data sets with millions of rows in it. Some of the individual submodels won't work at larger scales. So things like Gaussian processes, typically they have quadratic or cubic compute and memory requirements with the number of rows. So that they take effectively enormous amounts of time to run on larger data sets. So some of those we either automatically switch off or we sample randomly from the training data to give them a smaller data set to run on. For Gaussian processes, for example, we typically cap it at 1,000 rows just to keep it cheap and quick. And if you had a data set with 1,200 rows in, Gaussian processes might still be a very good model for that data set, or 2,000 rows, say, might still be a competitive model. We might still want to keep it in the ensemble without just throwing it out altogether. If you have 100,000 rows, it's not going to be helping. It's not going to be contributing much at that point compared to other models that can actually cope with data sets of that size. Part of the benefit of having a diverse ensemble means that we have algorithms in there that will cope with data sets of any size. Yeah, and Mario might want to weigh in more on some of the practical aspects of modeling very small data sets because he has a lot of experience of building our in-house models. I don't know if you want to add anything there, Mario.
Yeah, I guess with very small data sets, what you need is a different set of descriptors. So obviously, if you think about the spectrum of different models, then on one hand, you have the models which are dependent on data. So if you have more data, the models will become better and so on and so forth. And these are very fast models. Once you train them, they're really fast and they will give you answers for, I don't know, tens or hundreds of molecules within a second. And I guess on the other end of the spectrum, we have models which rely more on like physics, like maybe semi-empirical methods, or maybe even like ab initio methods. And obviously, these are very expensive models, and it takes a lot of time to run them. And I think when you do have a data set which is very, very small, then you have to rely more on these physics-based approaches and models which rely on maybe trained force fields specifically for your issues, or semi-empirical methods and so on and so forth. So it all depends on the descriptors, but I think the smallest model which I remember training, which has actually been useful, it was with 20 data points in the training set. But it was, first of all, it wasn't a global model, it was a local model. And second of all, it did require computational chemistry calculations to get the answer value. So yeah.
Thanks so much. Thank you both. So the second question I got is, does an ensemble include pre-trained deep learning models?
So this is an interesting question. So there are various kind of foundation models that people have built that are sort of pre-trained for large data sets, like the whole of Kemble, say, to predict various different properties, and then you fine-tune them for a specific task at the end. And the idea is to use sort of transfer learning to bring in that kind of general understanding of as much chemistry as you can get into the model, to bring that general understanding of chemistry and then fine-tune it for the specific task that you're trying to solve. So currently we don't include any of those models. It's something we're actively looking into, but there are various trade-offs inherent in including those kind of models in an ensemble because they're much larger than the standard models, and they have some of the same kind of limitations and strengths and weaknesses that every other machine learning model has. Like a big pre-trained foundation model will typically excel on tasks that are closely related to what it was trained on. But if you're trying to solve a problem that is much different from what it's trained on, it has limited relevance to that, then it's going to struggle because it's going to have to relearn a lot of what it's trying to do. There are also some really interesting sort of what's called in-context learning models that have come out in the sort of the last couple of years that we're looking at including that do some really cool stuff. Basically, they're a whole kind of new class of deep learning model that predicts data sets rather than data points. And we're actively looking at bringing a bunch of these things into the MetaModel process as we're going along. The design of the MetaModel ensemble is such that it's pretty trivial to add in a new model. It takes about 10 minutes to add a new algorithm in. It's built very modular and the machinery will just work. So we anticipate that we'll be able to keep this up to date with the latest machine learning models very easily in the future.
Thank you, Michael. So I got another questions for you. So someone asked, does the model automatically choose between MPN and RDKit descriptors and just RDKit descriptors?
Yeah, so it's one that I went backwards and forwards on exactly how we should handle this for some time. Um, there, I think that the end result is just that if um, we have to test effectively. We have to see if these are going to help. We can make assumptions based off the data, but we have to actually check whether the GNN descriptors are going to help for any given problem. And the way I would do that is with a validation set, add an additional stage to the training pipeline, and effectively just test or as part of our pipeline when we're building these models. Does adding the GNN descriptors actually help? Because the risk is that you're just adding more numbers in that aren't relevant to the problem you're trying to solve, and you end up with twice as many descriptors, twice as much overfitting, and a worse model at the end of it. But they are, on the other hand, they're so powerful on some problems, they really give a massive boost to performance. We do want to make sure that they are available because there's such a big boost in performance that's potentially there.
Thank you. And other questions. Have you considered using cross-validation when training submodels for the MetaModel ensemble?
Yeah, so cross-validation is the process of dividing your training set up into chunks and then swapping those chunks around. So you would train a model 5 times on 5 different train validation splits, and that means you've got full coverage of the training data set, and it gives you a more accurate metric at the end of the training process than if you just train on one random split, say. The downside is that you have to train the model 5 times over if you're doing a 5 times cross-validation split, which, if you're training on a giant data set and it's taking several hours, you may not want to increase your runtime by a factor of 5. So we have the option in there, and we will use it for smaller data sets where the compute cost is not significant. On a larger data set, it's less important anyway because your random split is going to give you a more representative sampling of the data set. You're not likely to get an unrepresentative sampling of a large data set by randomly sampling a fraction of the rows. It's also, we didn't use it in the paper, but K-fold or cross-validation is kind of essential for stacking, where you take the predicted values from the model and use those as additional features for another iteration of the modeling process, which can lead to significant boosts in performance. But it means that you have to have the predictions from the validation set for every out of fold predictions for every row in the training data. So this is another thing that we're looking at for smaller data sets where we can boost the performance and we don't care about the additional computational cost. Unlikely to be something that we use that much for larger data sets because, like I said, it is just that expensive and the benefit is smaller there.
Thank you, Michael. There's another question. Have you tried using stacking to improve the model performance?
Yeah. Yes, I touched on it just then. It is something that we are actively looking into, and it is built into some of the MetaModel pipeline now. So yeah, the idea there is you stack your complete model in layers and use the predictions from the first layer as input to the second layer, much in the same way that you would have layers in a neural network, but with a much larger modeling framework. And this works very well. The team behind the AutoGluon machine learning package wrote a paper on showing the effectiveness of this a while back. We do include this as part of our range of training options. Again, you're training the model repeatedly, so there are costs to that. That does increase the compute cost, and it may not necessarily be the right thing to do for every data set. And as I mentioned before, it requires cross-validation. So it requires you to train the model n times over to get coverage of the training data so that you can actually use those features without data leakage.
Thank you. Next questions. Do your methods recommend endpoint data transforms or apply them automatically? For example, IC50, change to PIC50 to bring data distributions closer to normal rather than skewed.
So we do in general do transformations to our data. It's outside the scope of this paper, and it's not really something that I've dealt with, but Mario might be able to answer this one in more detail for how we currently do this. I'm sure it's something that we'll be looking at when we're implementing the MetaModel in our products as well.
Yeah, this is definitely something we need to address in the future. Essentially, I don't think we should do it automatically. I think the end user should always know when their input or output gets transformed. But there are methods how to detect that, if that data, for example, is skewed or anything like that, and then maybe address this as a question to the person who's training the model. Like, we've noticed this is happening with your data. Would you like to transform it, and so on and so forth. But I think currently the person who trains the model has to take care of the transformation.
One thing that we do automatically for a lot of the MetaModel modeling is apply a standard scaler to standardize the data, because some algorithms, neural networks, for example, really care about the scale of your data points. They want things to be roughly between 0 and 1. So other algorithms, random forests, for example, don't care that you can have any size of data in there. But neural networks will perform a lot better if you have roughly normally distributed data points between 0 and 1.
Thank you both. I think this might be the last questions, considering of the time. So, how do GNNs cope with features they haven't seen?
I'm not sure I understand the details of the question.
Maybe I can specify. So say, for example, you have a functional group in a test set, which is not seen in a training set.
So they'll do something. They're unlikely to come up with like a big sort of spike in activity if they're exposed to a new feature, because it's unlikely to trigger the kind of pattern recognition, which is functionally what most neural networks are doing. They're looking for patterns. So if it's similar to a structure that it's already seen, that might cause some activation of the network, and you might get some features coming out. Most of the time, I would expect it just to not activate. It's more like I'm not seeing a structure that I've noticed is important for this property, rather than I've seen something new. Here's a giant spike in activation that is going to throw off all of your calculations.
Thank you. Thank you, Michael and Mario. That's all we have time for today. Any questions we don't have time to answer, we will try to follow up by email as soon as we can. Details of our next webinar will be available on the Optibrium website and LinkedIn page shortly, along with other helpful news and information to help transform your discovery. All that's left for me to do is to thank Michael and Mario for an insightful talk. Thank you all for coming, and we'll see you next time. Bye for now.